So let's suppose that we roll a pair of fair six-sided dice until you get doubles. Let t equal the number of rolls that it takes. So for example here, let's go ahead and verify that t is a geometric random variable. So for us, in order to check that something is geometric, we are going to look at the binary condition. And here, since we're looking for pairs, the dice either are or are not a pair. It's our binary condition. Our independent condition is that since we are rolling these dice each time, right, each trial has its own roll, we assume the results of previous rolls have no influence on future rolls. We can assume each time we roll the dice it is completely independent. Next up is our trial condition. We are looking for, here we are going until we obtain doubles. I'm just going to put the parentheses on, not parentheses, what are these called? Quotation marks on the until. Trials until we obtain the doubles. And then lastly is our success condition. Now notice it wants a pair of doubles here. So if I were to list out my sample space, right, I go here to 1, 2, 3, 4, 5, and 6. And then same thing on this side here, since I'm rolling two dices. Well, we know that there's 36 outcomes here, but really the pairs are going to be at 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So that means that we only have 6 out of 36 outcomes here that will be a pair. And so that means that our probability of success here is fixed. It's going to be a 1 in 6 chance. And now that we have verified our conditions, we'll say, and I'll write in a different color here, since conditions are met, we can say y is geometric with a probability of success as 1/6. So again, this is just a good preview for the inference unit that's coming next semester. We check our conditions, and then we have our since statement. Now, find p of t equals 3 and interpret this result in context. So p of t equals 3 would be the same thing as saying the trials until we get our first success, our first pair, would be 3. So I would write it as follows. So p of t equaling 3, I said y, oh well. But we would do 1 minus 1/6, and this would occur 2 times because the first success occurs on the third trial. So notice we have 2 failures, and then we have our first success, and that's going to give us approximately 0.1157. Now, in context, this means that 11.57% of the time in the long run frequency, it will take about 3 trials until we get our first success. And so after we roll, if we repeated this again and again and again, there's about an 11.57% chance that our first pair will actually come up on the third roll. Okay, so then let's look over here. In the game of Monopoly, a player can get out of jail free by rolling doubles within 3 turns. Find the probability that this happens. So if we want the probability it's within 3 turns, again, a picture of my sample space would look something like it either happens on the first turn, the second turn, the third turn, all the way up to some nth term here. Again, I don't know what this n is, or k, or y, or however you want to say it, but this is just some random value in which it stops. So I'm looking here of rolling doubles within 3. So if I'm looking at the within, I want this part of our sample space, which means I could just find the sum of these three probabilities. So as a probability statement, we're looking that y is within the first three, which would look like it happens in the first turn, it happens in the second turn, and it happens in the third turn. Right, so this is it occurs on the first trial, it occurs on the second, or it occurs on the third. And so the probability it occurs on the first trial would look something like, and I'm just going to do some quick math here, y'all. For the complement 1 minus 1, 6 will give us 5, 6. So that means if this first success occurs on the first trial, that means there were no failures to report, and we get our first success on the first trial. If it occurs on the second trial, that means we had a failure on the first trial and then a success on the second trial, or if it occurs on the third trial, we had failures for the first two turns, and then we had our first success on the third trial here. So when I sum this sample space here, or not the entire sample space, but this portion of the sample space, I will get some number that I don't know because I did not do my calculations ahead of time, but here's a good opportunity to look at the calculator. So you all know I'm anti-calculator, but I'm not anti-time efficiency. So we're going to go to second vars, and we're going to go where you hit the up arrow, and we're going to go, we notice you have two values here. A geometric PDF, and PDFs for any of these distributions give us the precise value, whereas the geometric CDF, and again CDF for any of these, is a cumulative distribution function, and cumulative here means adding up to. So I'm actually going to select this option. So my P was 1 over 6, and the X value is the first three. So we're going to take that, and that's going to give us about 42.13. So that's going to give us approximately 0.4213. And if I were to just do this with a regular old calculator, let's say I don't have a TI, that's totally fine. You don't need one to be successful if you are a mathematician, but we are going to do some mental math here. 5, 6 to the 0 is just 1, so I'm going to have 1, 6 plus the product of 5, 6 times another 1, 6. And I always do parentheses because your calculator reads PEMDAS. Then we'll have 5, 6 squared times another 1, 6. And theoretically, we should get the same answer of 0.4213. So as you can see, whether you have a fancy schmancy calculator or not, we are still able to find these probabilities. And then lastly, find the mean and standard deviation of this distribution, which means let's look at our parameters. So I want mu of y. This is what I'm looking for. This is what it means. This is what it looks like substituted into the equation. So if every 1 in 6 chances here of success, that means if I were to do this 6 times, hopefully we'd see 1 success here. So this would be about 6 rolls. Again, that context here, not just 6. 6 what? Elephants, cookies, sticks of dynamite? I don't know. So again, what am I looking for? What does it mean? What is the substitution? What is the answer? And what is our context? And then we're going to repeat the same thing for the sigma of y here. So we have the square root of 1 minus p all over p. So the square root here of 5, 6 divided by 1, 6 will give us approximately, and let's check it out. So the square root of 5 divided by 6 is some number, and that divided by 1, 6 will give us 5.4772. I'm just going to round here, so we'll call that 5.48 rolls. And again, you could be asked to interpret these parameters, but here's our center, here's our spread, and we know the shape, regardless, will always be skewed right. So that's just some examples of ways that we might see the geometric random variable presented to us in class or on the AP exam.